Boom. Hello, ladies and gentlemen. So here we are. We're taking a look at what I am going to call your COVID calculus. Come on, that was funny. That was cute. So COVID calculus, and we're going to start off with, I've got my notes here, so I just want to follow along. Calculus. So calculus is the mathematics of I spelled that wrong. Infinitesimal. That's a great word. Infinitesimal. So calculus is the mathematics of infinitesimal change. So that's what calculus is. It's the mathematics of really, really, really small change. Well, that word infinitesimal change is as close to zero change, so as close to no change at all, as close to zero change as you can ever possibly imagine. So an infinitesimal change is as close to zero change as you can ever possibly imagine, but, you knew there was a but coming, but not zero change. Now, this is our first day together, and you're going to have to get used to my writing. It's kind of a hybrid between what used to be called cursive and printing. And my Z's are weird. I getcha. You're going to have to deal with that. They look kind of like threes. That's a cursive Z. But this is infinitesimal change is as close to zero change as you can ever possibly imagine, but not zero change. Now, what I'm noticing is I'm writing on this paper, and I seem to be up and down and all over the place. So what I'm thinking is if I grab something that is going to keep me a little bit more organized. So maybe I'm going to write on here from here on in, because I got the little dots to keep me straight. So, calculus. I'm not repeating it. This is new. Calculus is dynamic rather than static mathematics. Here's an example of a static problem. Something you've done a billion times. What is the perimeter of a square with a side length of 2 meters? There you go. Oh, you can't see what I'm writing. Someone in my studio audience really should let me know this. There you go. So what is the perimeter of a square with a side length of 2 meters? That's a static problem. Everything's static. And what static means is not moving. Here's an example of a dynamic problem. And this is what calculus aims to solve. At what rate, or at what speed, speed and rate are the same thing, at what rate is the area of a square changing when the side length increases at a constant rate of 2 meters per second. Now look at those two questions. First of all, the first one's little. It's just a couple of lines. Next one's big. That's scary enough. But notice the first one, everything's just sitting there. The square's just sitting there waiting for you to do something to it. In this one, the square's moving. It's dynamic. The side lengths are changing. They're changing at 2 meters per second. So if you try to think of this square, you better think of a square that's getting bigger and bigger and bigger and bigger and bigger and bigger. You better not just be thinking about it at one point in time. And as it's getting bigger and bigger and bigger, its area is increasing, getting bigger and bigger and bigger. So calculus is the mathematics that looks at how is the area rate of change changing as the length is changing. Those are changes. That's dynamic. That's calculus. So, historically, calculus was developed. Now, that's a great discussion that we can have at some point, and we'll never get to the end of it. And it's something I'd like you to keep in mind for the rest of your life. Is math actually invented or discovered? That's a great question. Do humans create this mathematics, or do we discover it? Was it always there? And I'm going to tell you, I can argue both sides. It's a great question. So historically, it was developed. So notice I'm sitting on the fence here. I'm not saying it was invented. I'm not saying it was discovered. But the methodology of calculus was developed. It was developed to solve these three main problems in science. Number one, the tangent problem. And that really wasn't in science per se, like biology and chemistry and physics. That was also in math. So I'm including math as a science here. But to be honest with you, math is bigger than science. It's also philosophy. So where biology is not a science, it's not a philosophy and a science. It's a science. It's a pure science. Math, we would have developed calculus without any of the other sciences. Okay, just because it's math. But the tangent line does show up in the other sciences as well. Number two, physics. The physicists needed calculus because they needed to talk about instantaneous speed. They needed to talk about change that was happening right now, not average change. Average change is easy, but instantaneous change, what's happening right now. And that's a hard concept. Number three, the area under a curve. Now that's a purely mathematical area, a purely mathematical endeavor. However, it has huge implications in all of the sciences as well, depending what the curve represents. So these two represent a certain branch of calculus. There's two branches of calculus that you're mainly concerned with right now. One is differential calculus. And that's the calculus of derivatives. You don't know what that is. We'll get there. But that's the calculus of derivatives. And this is going to be integral calculus. And that's the calculus of integrals. Your parents, when they took calculus at school, when they talked to you about calculus, they did both in high school. You will only do one. You will only do differential calculus in high school. You will not do integral calculus in high school unless you take GLS or AP Math. It's not part of the curriculum moving forward, but you will definitely doing it first year university. So there's that difference there. Okay. That's calculus. That's what we're doing. Limits. We need to talk about limits. The concept of a limit is the foundation of calculus. Did I go too fast? Should I have gone back and shown you that we're okay? Okay, so it's the foundation of calculus. We need to be able to, we need the skills to be able to read, visualize, conceptualize, and compute various limits. You at home, you still have no idea what this limit is. I haven't even told you about it. Kids here, we've talked a little bit about it, and I'm going to make it clear to all of you in just a moment. But right now I'm going to tell you that limits, this thing called a limit, is this idea that's fundamental to calculus, and that we need to be able to read, visualize, conceptualize, and compute these limits. What does it mean to compute a limit? To compute a limit means to determine what happens to the value of an expression as the variable gets closer and closer but never equal to some particular value. Symbolically, because math has our own language, of course, this is what that means. And it is gorgeous. And it is your new mathematical animal. It's called a limit. Just take it in for a little bit, people. Just bask in its glory. It is glorious. And what we say, how we read this, is we say the limit of f of x as x approaches a value a. And that's what we call a limit. And isn't that just splendid? So there's a couple of things to notice here. This part is what we call the limit. But a limit is nothing without this part, which says that the variable x approaches a. But remember, this concept of approaching includes but never equals a. So I get to get closer and closer and closer and closer to a, but I never, ever, ever get to touch a. And this part here is your function that we're talking about. This is the function. And in fact, that's the y value. That's the range of the function, isn't it? So when I calculate f of x, this actually works out to its range. Its y value, if you will. We've talked about that a little bit. Now, I've talked to the kids in class, but I'd like to talk to the kids at home too about this concept of a limit, and I'm going to do it very briefly. There was a guy in ancient Greece. His name is Zeno. And back then they just had first names and where they came from. So it was Zeno of Elea. And this is a long time ago. This is about 460 to 430 BC. And he had a wonderful, wonderful quote. It was actually a paradox that he threw out there. And he said, To travel any distance, you must first travel half of it. And that seems so trivial at first. And everyone in the studio audience remembers how trivial that sounded at first. But it's a huge, huge problem. Because basically what he's saying, if we think about this, if we start somewhere, that's you and me, isn't that a great little picture? And let's say we want to go, I don't know, want to go home. And let's say that home is 4 meters away. So this whole thing is going to be 4, well, let's do miles, because if you're only 4 meters away, that's pretty sad. But anyway, and let's say that I wanted to get there. So what he's saying is no problem, you can go there, but your first step has to be to go half the distance. So you're going to have to go from here to there first. And that makes sense. And if I do a little chart of what's going to happen here, I'm going to travel my distance, my total distance that I'm going to travel, and then my delta D will be whatever's left over. Okay? So I'm going to travel half my distance, and that means I have 2 left over. So I've traveled half, I've got half to go, and that makes perfect sense. But now if I'm going to travel the rest of the distance, I need to travel half the remaining distance, which means I need to travel another 1 mile. So my total distance traveled is 3, and the amount that's left over is 1. And then I got to travel half that distance, so I got to travel 0.5. So I'm going to travel a total distance of 3.5, and I have 0.5 left over. And then I got to travel half that distance, which is 0.25. So that's 3.75, and what I got left over here is 0.25. And my pen seems to be running out, which is really, really sad. I got to go half this distance again, which is 0.125. So then this one would be 3.875. If I've made a mistake here, then correct it, but you know, I'm on video and give me a break. And so anyway, when we add these two together, I'm looking to my studio audience. Did I do them right? Oh, good. When I look at this, you're going to notice that my total distance that I travel plus whatever's remaining has got to equal 4, right? But the problem is I can keep doing this forever and ever and ever. I got to keep traveling half the distance. So as long as I can keep moving half the distance, like if I'm wearing a size 12 shoe, it's going to hard to move half the distance, right? I'm going to have to figure something out here. But as long as I can continue moving half the distance, I ain't ever getting there. It's just never going to happen. And we talk about that by saying delta D is going to approach 0, but it never, ever, ever does approach 0. There's always half the distance remaining. And as delta D approaches 0, as delta D gets closer and closer and closer to 0, we certainly do get closer and closer and closer to 4. But guess what? You're never, ever, ever going to reach 4. So that was kind of how annoying that guy was. And because if you think about this, then we can never get anywhere if we could always move half the distance. And this is the concept of a limit. So this concept, delta D approaching 0, would be represented in this notation by the limit, meaning it goes on and on and on and on. That's what the limit means, of delta D approaching 0. And that's what that stands for. So that's how that would be talked about. And then your function, of course, would be the distance plus delta D. And that would just be your function. And you're going to notice that that whole thing is the way that we would talk about this setup up here. So the delta D is approaching 0 as distance plus delta D. If that hurts your head a little bit, it should. I'll give you a video of some YouTube guys that talk about it maybe in a different way. But this is your first time hearing it. The second time will be better. The third time will be better. And yes, it's supposed to be a hard concept. But it's so simple that it is huge. A lot of implications here. A lot of implications to theology, to mathematics, to physics, to everything. Okay, so I'm going to flip over there. If you need that and I've flipped over and you're at home, pause the video. So where am I at? I'm talking about limits still. So there are different types of limits. There are different types of limits. And these include first type we're going to talk about today are one-sided limits. The next type we're going to talk about are two-sided limits. Wouldn't it be great if there were three-sided limits, but there aren't. So we've got one-sided limits, we've got two-sided limits. We're going to talk about infinity limits. We're going to talk about indeterminate limits. If I use a word you don't know, which indeterminate is one of them, indeterminate, learn how to spell it. It's important. We'll talk about what it means later on. I'm just right now, guys, you know nothing. So I've got to just start at the beginning and start using words and terms that you don't know, and we'll start building up our vocabulary. So this is indeterminate limits, and we're going to have limits that go to, or we're going to have limits, and we're going to say that do not exist. So I'm putting this in brackets because how can I have a limit that does not exist? It doesn't exist. But we're going to do limits that it's going to show that they don't exist, and we're going to have to talk about that. And we're going to go. And included in this will be limits that go to infinity.
So isn't the third one infinity?
No, that's nice. Yeah, hold on, I'll be right there. Limits that go to infinity. So there's a difference between infinity limits, which you brought it up, so I'll show it to you now. There will be limits where the variable goes to infinity. Those are talked about as infinity limits. And we're going to have limits that are going to go, and they're not going to exist, but they're going to go to either positive or negative infinity. And that's the difference. So there's a difference between a limit that goes to infinity and an actual infinity limit. But thank you for bringing that up, and I'm more than happy to talk about that there. But yeah, that is a difference. Good. Excellent. And while we're here, because you've brought that up, let's throw in indeterminate limits. And indeterminate limits will be a limit that has 0 over 0. And that concept of the word indeterminate means we don't know. And we'll talk more about that later on. But 0 over 0 is a bit of a problem because following one rule, anything multiplied by 0, which this could be shown as multiplication, right? 0 times 1 over 0. Anything multiplied by 0 is supposed to be 0. And we know anything divided by 0 is supposed to be undefined. And we know anything divided by itself is supposed to be 1. So I've got 3 different rules there that all could apply at once. So you know what we call it? Mathematicians are awesome. We call it indeterminate, meaning don't know. We got more work to do. Okay, that's what that means. So there's 3 different answers here, and we're not sure. We got more work to do. Okay, I'm just going to pause the video there just in case I goof up, and then I'm going to start at the end of this in the next video.